All right, let's jump right into the world of acids and alkalis. You might not realize it, but you're dealing with them all the time. In the food you eat, the soap you use, pretty much everywhere. So we're going to break down what exactly makes them tick.
Have you ever really thought about why a lemon is so sour? Or what makes soap feel so slippery? Well, it's not magic. It's pure chemistry. And the secret to both is all about this fundamental divide between acids and alkalis. So yeah, let's dive in.
Okay, so what are acids and alkalis really? When you get right down to it, it's all about these tiny little charged particles called ions. The whole game is about which type of ion a substance lets loose when you dissolve it in water.
And you know what? The main difference is actually super simple. Acids, they're all about releasing hydrogen ions. That's H+. Alkalis, on the other hand, they're the ones releasing hydroxide ions, or OH-. That's it. That's the chemical showdown. H+ versus OH-.
All right, let's get a little more specific with acids. Basically, an acid is any substance that kicks out those hydrogen ions when you dissolve it in water. A classic example you'll always see is hydrochloric acid, or HCl. The moment it hits the water, bam, it just splits apart, releasing those H+ ions and some chloride ions.
And then on the other side of the ring, you've got alkalis. Now, the key phrase to remember here is soluble base. So when an alkali, like sodium hydroxide or NaOH, dissolves in water, it does the same kind of splitting thing, but it produces hydroxide ions instead. Those are our OH- particles.
Okay, this is a super common trip-up, so let's clear this up right now. Are all bases alkalis? Nope. Think of it like this. Base is the big category, kind of like fruit, but alkali is a more specific group within that category, like citrus fruit. To be an alkali, a base has to be able to dissolve in water. So all alkalis are bases, but not all bases get to be alkalis. Simple as that.
All right, so we've established that acids and alkalis release these different ions. But how in the world do we actually measure that? I mean, you can't exactly see an individual ion floating around, right? So we need some clever tools to make the invisible visible.
And that's where the famous pH scale comes into play. It's a simple scale, usually running from 0 to 14. The rules are easy. Anything below 7 is acidic, anything above 7 is alkaline, and that perfect 7 right in the middle, that's neutral. Think pure water, and the further you get from 7, the more intense the acid or alkali is.
So how do we see the pH? We use something called chemical indicators. These are basically just special dyes that change color depending on whether they're in an acid or an alkali. You've probably heard of the classic litmus paper. It turns red in acid, blue in alkali. But there are others too, like methyl orange and phenolphthalein, and they all have their own unique color-changing tricks.
Okay, take a closer look at that chart for a second. Let's say I gave you an unknown solution, and you had to figure out if it was alkaline, but the only tool you have is methyl orange. You think you'd run into a problem?
Yeah, you totally would. And this is a perfect example of why you need to know your indicators. See, methyl orange is yellow in an alkaline solution, but it's also yellow in a neutral one. So if you get a yellow result, what does that tell you? Not much, really. You can only be 100% sure it's an acid if it turns red. The big takeaway here is you've got to pick the right tool for the job.
All right, let's get into something that trips up a lot of people. We're going to tackle two words that sound similar, and people often use them interchangeably, but in chemistry, they mean totally different things. I'm talking about strength versus concentration.
Okay, let's start with concentration, because it's the easy one. Concentration is just about how much stuff, the solute, is packed into the water. Think of it like making juice from concentrate. If you add a lot of concentrate and just a little water, it's, well, concentrated. If you add just a little bit of concentrate to a lot of water, it's dilute. It's all about the amount.
Strength, though, that's a whole different story. Strength isn't about how much stuff there is, it's about how it behaves. A strong acid, like that hydrochloric acid we mentioned before, completely breaks apart or dissociates in water. That means literally every single molecule of it releases its hydrogen ion. And check out that arrow in the equation. It only goes one way. It's a one-way ticket.
But weak acids, they're much more hesitant. They only partially dissociate. That means only some of the molecules are breaking apart at any given moment. And look at the arrows in this equation. They point both ways.
That's because it's a reversible reaction. The ions can actually get back together and reform the original molecule. That is the crucial difference between strong and weak.
Okay, so we know what acids are, we know what alkalis are. What happens when you put them together? Well, this is where the real action is. It's called a neutralization reaction, and it's basically the main event we've been building up to.
The official textbook definition is a reaction between an acid and a base that makes a salt and water. But if we zoom in and look at the ions, it's actually much simpler. It's all about that moment when the H+ ions from the acid finally meet the OH- ions from the alkali. So, let's walk through it with our examples. We mix hydrochloric acid and sodium hydroxide. Now you've got 4 different ions swimming around in the water. But here's the thing. The sodium and the chloride ions, they're not actually doing anything. They're just kind of hanging out, watching the show. That's why we literally call them spectator ions. So, if we just ignore them for a second, we can see the real reaction.
And what is that real reaction? It's just this. The hydrogen ions and the hydroxide ions combine to form H2O, water. When you strip everything else away, that's all that's happening. Kind of cool, right? It's that simple.
Now, neutralization is definitely the headline act. But acids are super reactive. They get into a bunch of other important reactions that you see all the time. So let's just quickly run through a couple of those. So besides alkalis, acids also love to react with things like metals, metal oxides, metal hydroxides, and carbonates. And in all of these reactions, the basic idea is the same. The acid's hydrogen gets kicked out and replaced, and you end up forming a compound we call a salt.
For example, you take an acid and you drop in a reactive metal like magnesium. What happens? You get a salt and you get hydrogen gas. You can literally see it bubbling away. And if you've ever been in a science class, this is the reaction that gives you that famous squeaky pop test with a lit splint.
Another really common one is an acid reacting with a carbonate. This time, you get a salt, you get water, and you get carbon dioxide gas. And this reaction is everywhere. It's what makes bath bombs fizz, and it's the classic volcano experiment you did as a kid with vinegar and baking soda. So let's just wrap this up by connecting it all back to the real world. I mean, these reactions aren't just in a lab, they're happening all around us. That acid-carbonate reaction we just saw, the carbon dioxide gas that pumps out is what makes a cake rise in the oven. That big neutralization reaction, it's used on a massive scale to treat acidic industrial waste. Understanding how acids react with metals is absolutely crucial for stopping rust on everything from your car to a giant ship. It really is a chemical world, and now you've got a much better handle on 2 of its biggest players.